Good afternoon, myself Pavitra. I am working as a Senior Facility Technologist at NNFC, SENS. I am going to give you a brief introduction on dry etching process. Okay. What do you mean by etching? Etching is nothing but a removal of a material from the substrate. Okay. So this etching technology is having two major techniques. One is the wet etching technology and dry etching technology. Wet etching, in wet etch, the people are using pure chemicals. By using chemicals, we are doing a pure chemical etching. When it comes to plasma, we are applying a RF power to a pair of electrodes for a etch chamber. Whenever we apply a RF power to the chamber, so the electric field is generated. So these electrons get accelerated by the electric field and gets a kinetic energy. So when with this kinetic energy, these electrons will collide with the molecules and atoms. Okay. So when these collides with the atoms and molecules, the ionization and dissociation takes place and the plasma generates. Okay. So this plasma is responsible for etching process. Okay. So that's why the dry etching is called a plasma based etching technique, and this etching is a combination of a chemical etch and physical etching. Okay. So if you consider the simple differences between the wet etching and dry etching process, the wet etch, the selectivities can be controlled by cleverly selecting the chemicals. Okay, there the major factor that involves is the chemicals. Okay, so by cleverly choosing the chemicals, we can control the selectivity. Okay, so but when it comes to dry etching, the selectivity controlling is little difficult, but can be tuned by varying a different process parameters or chamber parameters. Okay, so as I mentioned, wet etching is purely a chemical etch, so it prominent to give you a isotropic etch profiles. But in dry etching, since we have many parameters, many chamber parameters to control, we can achieve both isotropic and anisotropic profiles. Okay, these are the major differences between a wet etching and dry etching. In this, when we have both wet etching and dry etching, what is the need for dry etching? Okay, so dry etching is well suited for your release structures, since the wet etching is happening at a liquid phase. After releasing the structures, if you want to take out the structure, released structure from the liquid, because of the stiction, it might stick or something, you might lose your released structure, but that will not happen in the dry etching. So dry etching happens at a high vacuum chambers at a dry place, so that's why it is well suited for your released structures. And also, since it is, as I mentioned, it's happening at the high vacuum chamber inside, so the particle contamination is greatly reduced. Okay, and dry etching allows for precision endpoint control, because wet etching always you are the person are responsible for taking the sample from the solution once it reaches the end time. But in dry etching, that is not the case. In dry etch, what happens, the machine will take care of your endpoint, so the precision endpoint can be achieved in the dry etching. And also the dry etching is well suited for your single wafer processing. Then so now when it comes to pure dry etching, what is the etching process sequence happening? I think in the image you can see there are multiple things are happening. About 6 steps is taking place to complete the etching process. These are, now I think you can see there is a RF power we have applied to the chamber electrodes, and meanwhile we are passing some gas onto the chamber. Okay. So now once there are gas molecules inside and electric field, there is a ionization and dissociation. So because of this ionization and dissociation, your plasma is generated. So in this plasma, you have equal number of ions and radicals. So now this is the first step, is generating a reactive species. That means your ions and radicals. Next step is these ions and radicals are diffused into your substrate surface. Once it diffuses onto the surface, the next step is adsorption onto the surface. After adsorption, now the reaction is taking place on your substrate with the material. Once the reaction takes place and it will generate a volatile byproduct, then the desorption of volatile byproduct will happen, and after that this whatever the volatile byproduct has dissolved, that will diffuse into the bulk and then it will come out of the chamber. Okay, these are the major steps which follows to achieve a dry etching process. In dry etching technology, we may have a plasma etching, that means only the chemical etch, that is also called as a plasma assisted chemical etching. I think in the images you may see we have only radicals in the plasma. So whenever you have only radicals, it's almost a chemical etching. So since it is a chemical etching, you tend to get anisotropic profiles. Okay, so that is called a pure chemical etch or a plasma assisted etching. The next thing is a physical sputtering. So this is, here we don't have any kind of radicals, we have only ions. These ions are responsible for the physical bombardment. Okay, so the example what we have nowadays techniques are maybe ion milling, plasma sputtering. These are examples for the plasma sputtering. Here the substrate damage is more, and also you will get an anisotropic profile, but you are not able to control the angle or profile here because the ions are responsible for your physical etching. Okay, now to overcome the disadvantages of these two, we have come up with a technique called reactive ion etching. Okay, so reactive ion etching method is a combination of both chemical reaction and an ion bombardment. I think you can see in the last image we have both ions and radicals in the plasma. These radicals are responsible for your chemical etch and ions are responsible for your physical bombardment. That's why the reactive ion etching is also called as ion assisted etching. Okay, so by controlling both chemical etch and the ion bombardment, we can always achieve a highly directional anisotropic profiles. I think you understood how the dry etching process sequence is taking place, and also what are the different dry etching processes. Now there are some terminologies you need to understand in dry etching. In that, the first thing is the etch rate. As I mentioned, the etch is how much the etch rate is the material to remove from the substrate. So the etch rate is how much material you are removing from the substrate in a given time. That is your etch rate, that can be calculated by using a given formula. And then the next term what we have is selectivity. Selectivity is a very important terminology or important criteria in dry etching. This selectivity can be defined as the ratio of the etch rates of a different material. That might be a etch rate of the mask to the etch rate of your material. So selectivity can be always tell that the ratio of etch rate of the resist or a mask to etch rate of your film. Okay, so always the etch rate of the mask material should be less compared to your etch rate of your material. Then only you can achieve a desirable depth by keeping your mask material. Okay, so that is the selectivity. And then other than selectivity, we have profiles. In profiles we have isotropic profile and anisotropic profile. I think isotropic profile, the etch rates are same in both vertical and horizontal direction, but in anisotropic etching the etch rate will be different in horizontal and vertical direction. Okay, so next what we have is uniformity. So whenever you are doing the etching, the uniformity across the wafer is also important. That can be calculated by using this formula. Other important thing is a loading effect. What do you mean by loading effect? So I think in the images says clearly the loading effect is nothing but we'll always get an etch rate difference between the densed patterns and isolated patterns. Okay, so why in the densed patterns the consumption of species will be more than the isolated area. So that's why whenever you have a different design on your same substrate, like in one place you have a dense patterns and one place you have isolated patterns, always you will get a etch rate variation from dense pattern to isolated patterns. This is mainly due to the local depletion of your species, reactant species. So that's why before whenever you are going to design your mask, always your design should be spread uniformly across your wafer. Okay, so or else you will face this loading effect issue, and you will end up with different etch rates on the same design, same wafer. Okay. Then dry etching chemistries. We have a fluorine based chemistry and we have a chlorine based chemistry. Mainly fluorine based chemistries are used to etch your dielectric materials, and chlorine based chemistries are used to etch your metals. Okay, and also we have some mixed chemistry to etch a silicons, so that can be used to get a highly directional anisotropic profiles. So it's like when a dry etching, so when it comes to chemistry, the important is you are getting a volatile byproduct. So whenever you choose your material, and maybe you will come up with this material saying that I have this material and I wanted to etch, then we will check with what are the gases we have. So is it this material is giving a volatile byproduct with this particular gas, then only we will going forward for etching, because getting a volatile byproduct is a very important in the dry etching process. So that's why we have different chemistries for different materials. It's like a fluorine based chemistry for most of the dielectrics and chlorine based chemistry for most of the chemicals. Okay, so I think these are some of the examples you can see. I think in the fluorine based chemistry we have SiO2 and silicon nitride etch by using CF4 gas. CF4 gas, when it splits into when it gets dissociation, so we will get with a CF3 ion and F radical. Now this F radical is responsible for your chemical reaction, so that's why F reacts with SiO2 and it will form a SiF4 volatile byproduct. So here what happens first, the silicon and O2 will get splits, then the silicon reacts with fluorine and it will form a SiF4 volatile byproduct. Same thing happens with your silicon nitride. Same way the chlorine is used to etch aluminium and titanium. So maybe the chlorine, when chlorine dissociates, it will give you only radicals, chlorine plus chlorine, Cl plus Cl radical. This radical reacts with purely with a chemical reaction, it will react with aluminium, it will form a AlCl3 volatile byproduct. Same thing with the Ti. So here I think you are seeing you don't have any ion here. So to get an ion assisted energy, most of the techniques, they will add some of the argon to the chamber, so that your argon ions acts as a argon ions will help for your physical bombardment. Okay, so and also we have some mixed chemistry. When you use SF6 to etch silicon, it will form SiF4, but you will end up with the isotropic profiles. Same with SF6 gas, if you want to achieve an anisotropic profile, we are going to add something called a C4F8 gas into the chamber, so that here C4F8 acts as a polymer and it will passivate your side walls, so that we can get an anisotropic profiles. Okay, same thing with the Cl and chlorine gas with silicon. When the chlorine radical reacts with silicon, it will form SiCl2 volatile byproduct. Okay, these are the different chemistries we are using in dry etching process. Now, as I mentioned, the ICP RIEs, RIEs reactive ion etching. So nowadays, earlier we used to have only RIEs like only with a lower electrode which is connected to an RF power, but there, because only with the one RF power which is connected to the bottom electrode, it was very difficult to control both ion energy and the density of the plasma. So to avoid that, they come up with an ICP RIE, that is inductively coupled plasma chemical reactive ion etching. So I think this is the schematic of the ICP RIEs. So what happens here, as usual, the bottom electrode is connected to an RF power. Along with that, the top electrode is also connected to a RF power with a different RF power, but that RF power is applied to a magnetic coil. Okay, so when they apply RF power to the magnetic coil, it induces a magnetic field and then it will generate an electric field, so that we can always control the directionality, and also we can increase the plasma density of the plasma. So that's why the key tool specs for the ICP RIEs are the etch rates can be high because of the density of the plasma, and also we could have a very good control over the selectivity and damage of the substrate, and also we have separate RF and ICP generators to control the ion flux and the density of the plasma. And low pressure processing, we can process at the low pressures with a high density, and also it's a chemical and ion induced etching, and can also be run in only RIE mode. Without applying any ICP power, we can work with only RIE mode. So this is the specs of the ICP RIE tools. So now whatever the RIE tools, reactive ion etching tools are there in our clean room, all are ICP RIEs. So this is one of the ICP RIE tool at our SENS NNFC. So this is a fluorine based tool, and also next to that we have a chlorine based tool. So again the fluorine based tool is dedicated to etch all our silicon, germanium, oxides, nitrides and all like dielectrics, and these are the gases which are available, fluorine based gases which are available in the RIE fluorine tool, and this tool is level 3A. That means we are not allowing any etching of the metal or metal exposed to plasma is not allowed in this tool. Okay. Same way we have RIE chlorine tool. So it's a level 3 tool. The metals can be allowed and metal etching is allowed. So here again we use to etch all our compound semiconductors and along with the metals, and these are the chlorine and fluorine based gases available in the tool. Okay. And this is the I was telling you, right, we have an isotropic profile, we have an anisotropic profile, and this is one of the SEM image we have taken from RIE fluorine tool. This is the SiO2 profile where we have around 120-degree angle, and this is the silicon nitride profile. These are all the anisotropic profiles. But this is a silicon etch where I told you we can use C4F8 gas for the as a polymer, and we can protect the side walls, passivate the side walls. By doing that process we can achieve a 90-degree profile and highly directional anisotropic profile. Okay. So this is one of the SEM image of silicon etch using RIE fluorine tool, and this is the isosilicon etch. I was telling, if you are not using any C4F8 and you are using only silicon to etch, if you are using only SF6 to etch silicon, always, since because of it's a pure chemical etch, you will end up with isotropic profile. This is one of the isotropic profile we have achieved in a RIE fluorine. And another ICP RIE tool is nothing but an RIE X. So it's a level 4 tool because it's this tool is dedicated to etch PZT. So it's a lead contaminated tool, and these are the gases, both fluorine and chlorine based gases which are available. So whoever is not bothered about the PZT contamination, that lead contamination, they can also etch all other materials like SiO2, silicon, nitride and all. So along with that, these are some of the materials. Al2O3 barium BaTiO2 and SrTiO3 are materials which are etching in this particular tool. This is one of the PZT etching profile in RIEX, and this is the aluminum nitride etch in RIEX tool. Along with this RIEs, we have also called as a plasma asher. So this is a small equipment where we use to remove a photoresist from the substrate. Okay, so maybe after your etch process you want to remove your photoresist as a mask, what you have used, that mask can be removed by using plasma asher. This is not only for that, maybe before going to do your etch process, if you want to do some DESCOM process, DESCOM is nothing but it's like by using very low power with the oxygen gas we do O2 DESCOM process. So here what happens after your litho process, if it is there any masking like undeveloped photoresist regions, suppose it might developed or it has not come out of the solution, it is still there on your substrate. if without O2 discum, if you go for a etching, that whatever the resist particles are there, that might act as a mask for you. So to avoid that, what we'll do is, with a low power oxygen plasma, we'll do O2 discum. So that time what happens, if it is there any kind of photoresist or any particles, it will get rid of it, and then our etch region will become clear for etching. Okay. So again, these are some of the materials which can be allowed in this tool, and some of the materials which cannot be allowed in this tool, and the gases available in this tool is only O2, argon, CF4 and nitrogen. Maybe along with your RIEs, we have also something called a deep reactive ion etching, so DRIE. So here the tool is mainly for silicon etching, and this contamination level is again 3A, so there is no metal etching and metal exposure to plasma, and the gases available here is SF6, C4F8 along with O2. And next, so DRIE, so what is the advantage of DRIE applications? If you see, it's a deep reactive ion etching, and it enables faster etch rates and the formation of deep trenches. It's a highly anisotropic etch profile that results in highly anisotropic etch profile and high etch rates with a high aspect ratios. Okay, so applications mainly you will use it in MEMS and NEMS etching, and also through silicon via for usage in advanced 3D and IC productions. Okay, so DRIE. So how can we achieve such a deep, and I was telling TSV means through silicon via. So if you have some around 570 microns of silicon, so we can completely etch 570 microns of silicon and we can do a through hole. Okay, so how it is possible? That is because of Bosch process. Okay, what do you mean by Bosch process? It's a Bosch process is a cyclic process where the separate deposition and etch will take place in different cycles. I think you can see the images. I think the first step is the photoresist as a mask you have, and this you have a substrate. Now my first cycle is an etch cycle. Always it will start with a etch cycle and end with the etch cycle. Now in etch cycle what happens? I'm going to apply only an SF6 gas. So in this what happens, as I told you already, only SF6 with silicon always form a isotropic profile. I think you can see in the image we have a isotropic profile started, but immediately we will switch to a passivation step. When you switch to passivation step, we are using C4F8 gas. I think you can see the C4F8 is coated on the walls and also on the bottom etch bed. So now the next process after passivation will switch for etch process. In that etch process what happens? First the SF6 whatever the radicals or ions is coming, that will clear the etch bed first, and then it will started etch deeper. But still your side walls are protected, because in etching always the vertical etch rates are more compared to your lateral etch rates. So by the time you remove your bottom masking, still you will have a passivation on the side walls and it will go little deeper. So but if you go more deeper, you might have lose your passivation on the walls. To avoid that, quickly we will switch to again a passivation layer C4F8. Like this, by keep on switching between a etch process and the depot process, you can keep protecting your passivation side wall and you can go deeper. Okay, so final step will be the etch step with SF6, so that all of the polymer which is coated on your side walls and bottom will be removed. So but what happens, since it is going first, it is having an isotropic and then the polymer is coating, so you will not get a smooth side walls. Always you will have something called a scallops. Okay, so whatever the shape you are seeing, that is called a scallops. Okay, so this scallops can be controlled by varying different process parameters. Example, we can control the power what we are applying, and we can control the switching time between the etching and the deposition. By controlling different process parameters, we can have a control over the scallop size. And also depending on your application, what is the application, depending on your application we can choose the recipe for your devices. And DRE again, it's a aspect ratio dependent etch. What do you mean by aspect ratio dependent etch? So the bigger features etch faster compared to smaller features, because if you see the ion flux is less in smaller features compared to bigger features. So that's why you will have a higher etch rates at bigger features and smaller etch rates at the lower etch rates at the smaller features. Okay, so that is called an aspect ratio dependent etch. I think you can see an image where you can see the bigger features etch more and the smaller features you having a lower etch rate. These are the some of the deep reactive ion etching images we have done in our DRE tool. I think till now you have seen all the etching processes and etching tools, right? So along with that we have a CVD also, a chemical vapor depositions. Okay, so let's see what are the chemical vapor deposition tools we have. So first of all, what do you mean by a chemical vapor deposition? So it's CVDs is nothing but chemical gases or wafers react on the surface of the solid and produces a solid byproduct, okay, on the surface in the form of thin film. So this is nothing but a CVDs. CVDs will do this. So whatever the volatile byproducts will come, it will leave from the surface. So in this what we have is a PECVD, plasma enhanced chemical vapor deposition. That means in this PECVD the deposition process is accelerated by plasma. Okay, it enables high deposition rates at low temperature. If you see other conventional CVDs like LPCVD, APCVD and all, so at higher temperatures the chemical reaction is taken place. There the process driven is by the temperatures, but here the process is accelerated by or driven by a plasma generated in the chamber. Okay, so I think as I explained how the process sequence is taking place on the etching process, I think the same way the deposition process will also takes place, but here what happens, first the reactant species or reactant enters into the chamber, that means the gases will deliver into the chamber. The second step, the dissociation of the reactants will happen by the electric field, and then the film precursors will form. Whatever the gases we have sent, depending on that the film precursors will form, and then these precursors will adsorb onto the surface. Then they will start diffuse into the substrate, and then the surface reaction takes place. Once the surface reaction takes place, the continuous film will form. Okay, so then whatever again the byproducts will come, that byproducts will come out of the chamber by using exhaust. Okay, so again here the same thing. So plasma generation is same thing. We have we have two pair of electrodes. We will apply electric power to that, RF power, radio frequency power, so that the electric field will generate. Because of that the plasma will generate. Here again the different parameters can be controlled. The etch process is gas compositions what you are using, that, and also the gas flow, temperatures, at what pressure you are doing, and also what is the frequency of RF power you are applying, and also the RF powers. Okay, and now PCVD. This is the PCVD tool at Sense, the plasma enhanced chemical vapor deposition tool. So the equipment capability, we are able to deposit a silicon nitride, silicon dioxide, amorphous silicon and polysilicon, and also germanium, and precursor gases available is the following like silane, germane, CH4, ammonia, CF4 and nitrous oxide, and also we have some carrier gases and also doping gases, so B2H6 and phosphine. Along with PCVD we have ICP-CVD. So again ICP-CVD is inductively coupled plasma chemical vapor deposition tool. So here again the materials can be deposited is SiO2, silicon nitride, oxynitride, and also we can do a void free SiO2 trench filling. Okay, so these are some of the materials allowed into the tool and some of the material not allowed into the tool. Again the parameters which involves in the process are by optimizing the process, for optimization of the process the parameters can be tweaked is the substrate temperature, the chamber pressure, RF power, ICP power and gas flows. Okay, So I think now you have seen both PECVD and ICP-CVD. What are the difference between PECVD and ICP-CVD? Both are plasma enhanced chemical vapor depositions, but the difference is PECVD is, this is the schematic of the PECVD. I think PECVD, you can see only the top electrode is connected to a 13.56 megahertz of RF power and bottom electrode is grounded. Okay, so here what happens, the density of the plasma will be low compared to ICP-CVD, but in our ICP-CVD, like same way in the ICP-RIs, we are applying an ICP power, the separate RF power to the top electrode for the magnetic field, so that the density of the plasma will be very high in the ICP-CVD compared to PECVD. Since because of the plasma density, the density of the film, the quality of the films you are getting will be different for PECVD and ICP-CVD. So in PECVD, one of the advantages, since we can switch between two different RF powers, HF power and high frequency and low frequency, we can control the stress of the film. Okay, so and also we can have a low temperature process compared to our other conventional CVDs. But ICP-CVD is again here, since we have a both ICP and RF power, we have an independent control on our ion energy and ion current density. So the ICP-CVD enables depositions at high quality dielectric films at low temperature with a low damage. So if you see, consider the films deposited in PECVD and ICP-CVD. Just one of the example is the SiO2 film can be deposited using silane and nitrous oxide in PECVD. That wet etch rate is of that SiO2 film is 200 nanometers per minute. And the SiO2 film which is deposited in ICP-CVD by using silane and O2, this is because of the high density plasma, the densification of the film is good and the quality of the film is good, so that the wet etch rates can be achieved 120 nanometers per minute. These are the major differences for PECVD and ICP-CVD. The quality of the film may differ from PECVD to ICP-CVDs. Okay, thank you.